Right now, there is a star in our galaxy so large that if you put it where our sun is, it wouldn't just swallow Earth. It would swallow Mars, the asteroid belt, Jupiter, Saturn, all of it gone. Buried inside the outer atmosphere of a single star. That star is called Stephenson 218. It's real, it's out there right now, and the more precisely we try to measure it, the more uncomfortable the numbers get. Not because the star is dangerous to us, it's 19,000 light-years away, but because it sits at the edge of what our models say should be physically possible, and it doesn't seem to care. By the end of this video, you'll understand how we found this thing, why measuring it is so difficult, and what it actually implies about the limits of stellar physics. And there's one fact about this star, something almost nobody talks about, that makes all the size comparisons look secondary. Quick version of how stars work, because you need it. A star is a balancing act. Gravity pulls inward. The energy from nuclear fusion pushes outward. These two forces find an equilibrium, and the surface where they balance, that's the edge of the star. For most of a star's life, that balance is stable. But when the hydrogen fuel in the core runs out, the balance breaks. The core contracts. The outer layers, still rich in hydrogen, start fusing in a shell around it. That shell dumps enormous energy into the envelope. The star inflates, sometimes to hundreds of times its original size. The surface spreads out, cools down, turns red. That's a red giant. And in the most massive stars, that process doesn't stop. The core keeps heating up, keeps fusing heavier elements, keeps pushing the envelope outward. Eventually, you get what astronomers call a red supergiant, a star whose outer layers have expanded so far from the core that the whole structure is more like a diffuse cloud than a solid sphere. The theoretical upper limit for how large these things can get was, for a long time, thought to be around 1,500 times the radius of our Sun. Beyond that, the radiation pressure should exceed the gravitational pull on the outer layers, and the star should start destroying itself. Stephenson 2-18 is 2,150 solar radii. But before we get into what that actually means, we need to talk about the stars that came before it. Because the story of how we found this one is, in a lot of ways, a story of getting things wrong. For most of the 20th century, the largest known star was Betelgeuse. You know Betelgeuse, the bright red dot in the shoulder of Orion. Close enough, about 700 light-years away, that we can resolve its surface directly. It's been observed, measured, and remeasured more times than almost any other star. Its size estimate has landed at around 700 solar radii, depending on the method. If you replaced the Sun with it, its surface would reach past the orbit of Mars. That sounds enormous, and it is. But Betelgeuse has one major advantage over the other stars on this list. We can actually see it properly. It's nearby, it's not obscured, and our measurements of it are relatively clean. Everything gets harder as you go further out. In the early 2000s, the leading candidate for largest known star was VY Canis Majoris, a red hypergiant about 3,900 light-years away in the constellation Canis Major. Studies published in 2006 and 2007 put its radius at around 1,800 solar radii. That would make it large enough to engulf Jupiter's orbit entirely. The problem: VY Canis Majoris is a mess. It's surrounded by an enormous asymmetric nebula, clouds of gas and dust that the star has been violently ejecting for centuries. When you're trying to determine where the stellar photosphere ends and the surrounding debris begins, the answer is not obvious. Different studies made different assumptions about the nebula's contribution and got very different answers. By the time the measurements were refined, the estimate had dropped to around 1,420 solar radii. Still huge, but no longer the clear record holder. And then VY Canis entered the conversation, which is where things got genuinely complicated. VY Canis sits in the constellation Scutum, toward the inner edge of the Milky Way. It was first catalogued in 1860 at the Bonn Observatory. For most of the century that followed, it was nothing special, just another variable star in a long list of variable stars, noted and filed. What changed was the instruments. By the 2000s, improved spectroscopic analysis let astronomers take a much harder look at distant stars in this region of the sky. And when a team led by researchers at the University of Granada analyzed VY Canis in 2013, the distance estimate they arrived at was roughly 9,000 to 9,500 light-years. Applied to the star's observed luminosity, that distance implied a radius of around 1,700 solar radii, give or take 200, because the uncertainty was significant. 1,700 solar radii, larger than the revised estimate for VY Canis Majoris. The new record. VY Canis became the star that made it into every largest known stars video for the next several years. It was the poster child, the one everyone used as a benchmark. But here's the thing. The uncertainty never went away. VY Canis sits within what astronomers call the zone of avoidance, a band along the galactic plane where the dense gas, dust, and stars near the center of the Milky Way absorb and scatter the light of anything behind them. Studying a star through thousands of light-years of that interference is like trying to read a document through a wet paper bag. You can get information out of it, but every piece of that information carries errors, and those errors compound. The 2013 distance estimate was the best available at the time, but everyone involved knew it was provisional. In 2018, the European Space Agency released the second major data catalog from its Gaia spacecraft, a mission specifically designed to measure stellar distances with far greater precision than had previously been possible. And among its results was a new parallax-based distance estimate for VY Canis. Not 9,000 light-years, closer to 5,000. If Gaia was right, VY Canis was only about half as far away as the 2013 estimate suggested, which meant its actual radius was closer to 755 solar radii. Still a large star, not a record holder. The Gaia result wasn't definitive. Parallax measurements in the zone of avoidance carry their own uncertainties, and the scientific community didn't immediately abandon the previous estimates. But the record was, officially, in dispute. The throne was open, and something else was already in the data. The region of sky toward Scutum, in the direction of the galactic core, is one of the densest and most complex parts of the Milky Way visible from Earth. It contains multiple massive star-forming clusters, dense groupings of young, hot, and often enormous stars that formed from the same giant molecular cloud over the same general period. One of the most extreme of these clusters is called RSGC2. Also referred to informally as Stephenson 2, after astronomer Charles Bruce Stephenson, who compiled near-infrared stellar catalogs in the late 20th century. RSGC2 sits roughly 20,000 light-years away, and contains more than 24 confirmed red supergiant stars. It's one of the highest concentrations of massive evolved stars found anywhere in the local galaxy. Stephenson 2-18 was cataloged as a star in this region. Bright, variable, clearly notable. But there was a problem with it. It was too luminous. When you assume a star belongs to a cluster at a known distance, you can use that distance to calculate how much energy the star is actually putting out. And for Stephenson 2-18, the number was significantly higher than any other red supergiant in the cluster. High enough that some researchers suspected it wasn't actually a cluster member, that it might be a foreground object, a smaller star that happened to lie in the same line of sight, but much closer to Earth, making it appear artificially bright. That was a reasonable hypothesis, and it meant the star was largely set aside while more tractable targets got attention. The question of membership wasn't resolved until researchers took a different approach, measuring the star's radial velocity. Instead of trying to determine distance through brightness alone, they measured how fast the star was moving toward or away from Earth using the Doppler shift in its spectral lines. If Stephenson 2-18 was a foreground object, its velocity would be different from the cluster. If it was a member, it would be moving with the cluster. It was moving with the cluster. That settled the question of membership, which meant the luminosity was real, which meant the size implied by that luminosity was real. A team of researchers applied the star's luminosity and surface temperature to the standard equations for deriving stellar radii. The surface temperature was estimated from the star's spectral type, a classification based on the pattern of absorption lines in its spectrum, which corresponds to a specific temperature range. From luminosity and temperature, you can calculate the surface area required to produce those outputs. From surface area, you extract the radius. The result was 2,150 solar radii. They checked it. Then other groups checked it. The number has been refined slightly in subsequent studies, but no serious revision has brought it down enough to challenge the conclusion. As of now, Stephenson 2-18 is the largest star we've found. Okay, 2,150 solar radii. Let's actually deal with that. The radius of our Sun is about 696,000 kilometers. Earth's diameter is 12,700 kilometers. You can fit 109 Earths lined up across the face of the Sun. Most people know the Sun is big. This is not about the Sun being big. Multiply that solar radius by 2,150. You get a star with a radius of roughly 1.5 billion kilometers. The distance from Earth to the Sun, the entire span of space that separates our planet from the star it orbits, is 150 million kilometers. That distance fits inside Stephenson 2-18's radius about 10 times. Mars orbits at 228 million kilometers, inside the star. The asteroid belt peaks at around 480 million kilometers, inside the star. Jupiter orbits at 778 million kilometers, inside the star. Saturn, with its rings, its moons, the whole system, orbits at about 1.4 billion kilometers. The surface of Stephenson 2-18 would reach almost exactly to Saturn's orbit. Everything from the Sun to Saturn, gone. The volume that corresponds to is roughly 10 billion times the volume of our Sun, not 10 billion times the diameter. The volume. If you wanted to fill Stephenson 2-18 with copies of the Sun, you'd need 10 billion of them. A commercial aircraft flying non-stop at cruising speed would take about 19 years to circle the Sun. To circle Stephenson 218 at the same speed, roughly 1,100 years. You would have had to start in the early medieval period to finish today. Light circles the Sun in 14 seconds. Light would need more than 8 hours to circle Stephenson 218. That's the scale, and most people stop there. But the scale isn't even the strangest part. Here's the thing nobody talks about. A star this large should be extraordinarily massive, right? All that volume has to be filled with something. And Stephenson 218 is massive. It's estimated at somewhere between 12 and 15 times the mass of our Sun. That's a lot of material. But 12 to 15 solar masses spread across a volume 10 billion times larger than the Sun produces a density that is, frankly, absurd. The average density of our Sun is about 1.4 grams per cubic centimeter, similar to water, dense enough that it behaves like a solid from a distance, even though it's entirely plasma. The average density of Stephenson 2-18 is estimated at something in the range of 0.000001 grams per cubic centimeter. That's roughly 100 million times less dense than the Sun. To put that in terms, you can feel the outer layers of Stephenson 2-18 are less dense than the best laboratory vacuum we can create on Earth. You could fly a spacecraft through the outer envelope of this star and barely notice the resistance. The atmosphere of the largest known star is thinner than anything we've managed to produce in a lab by removing air from a sealed chamber. Which raises an obvious question. What is actually holding it together? The answer is that at this scale, held together means something different than it does for a normal star. The outer layers of Stephenson 218 are so loosely bound to the core that the star is constantly losing mass, bleeding material into the surrounding space with every pulse of the interior. The boundary between star and not star is genuinely unclear. There's no hard surface, no clean edge, just a gradient from extremely thin plasma to slightly less thin plasma, all the way down to the dense fusing core, thousands of solar radii inward. This is part of why measuring the star is so difficult. You're not measuring a sphere, you're measuring a cloud with a hot center. And the definition of radius becomes somewhat philosophical when the object in question doesn't really have a surface. Here's where the physics gets genuinely interesting. There's a concept in stellar astrophysics called the Eddington luminosity limit, named after Arthur Eddington, who worked out the math in the early 20th century. The idea is straightforward. A star produces radiation from its core. That radiation exerts pressure on the gas in the outer layers. If the radiation pressure gets strong enough, it overcomes gravity and starts pushing the outer layers away. Beyond a certain luminosity, a star can't hold itself together. It drives mass loss faster than gravity can compensate. For a star with the mass of Stephenson 2-18, the Eddington limit corresponds to a luminosity of roughly 300,000 to 320,000 times that of our Sun. The observed luminosity of Stephenson 2-18 is estimated at around 440,000 solar luminosities. That's significantly above the limit. Now, this doesn't mean the star is impossible. The Eddington limit is a simplified model. It assumes a uniform, spherically symmetric star with standard opacity. Real stars are more complicated. The outer layers can have different opacity in different directions. There can be convective structures that transport energy more efficiently in some regions than others. There are known examples of stars that appear to exceed the classical Eddington limit without immediately destroying themselves. But Stephenson 2-18 exceeds it by a meaningful margin, and that does require an explanation. The most likely explanation involves the structure of the outer envelope. When a red supergiant expands to this extent, the outer layers become so loosely bound and so irregularly structured that the standard Eddington calculation no longer applies cleanly. The radiation leaks out through lower opacity paths. The star isn't being held together in the same way a compact star would be. It's more like a very loosely organized cloud that's gradually dispersing at the edges while maintaining fusion at the center. This is consistent with what we observe. The star does lose mass, constantly. The question is whether it's losing mass fast enough that the luminosity figure we're calculating is actually correct, or whether the mass loss itself is affecting our luminosity estimates in ways we haven't fully accounted for. Researchers are still working through this. The honest answer is that the physics of objects at this extreme is not fully understood. And Stephenson 2-18 is one of the main reasons why. What happens next to Stephenson 2-18 is, in broad strokes, predictable. It's in the late stages of stellar evolution, fusing heavy elements in a core that's running out of options. At some point, the core will reach iron. Iron fusion absorbs energy rather than releasing it. The outward pressure collapses. The core implodes in a fraction of a second, and the outer layers, no longer supported, fall inward and then rebound in a shockwave that we call a supernova. When Stephenson 2-18 goes supernova, and it will, though the timescale is uncertain, probably within a few 100,000 to a few million years, it will be visible from Earth, possibly visible in daylight. At 19,000 light-years, it's far enough that the radiation won't be dangerous, but close enough that it will outshine everything in the night sky for weeks. But between now and then, the star may change significantly. Some red supergiants at this stage of evolution transition into yellow hypergiant phases. The outer layers contract slightly. The surface heats up. The star gets more extreme in a different direction before its final collapse. Others remain red supergiants until the end. Stephenson 2-18 is young enough, in stellar terms, that the current size may not be its maximum. That part is genuinely uncertain. Here's what the story of Stephenson 2-18 actually tells us, beyond the size itself. We found this star by accident, essentially. It was in the catalog. It had been sitting there as an unresolved anomaly for years, too bright to make sense, set aside while other targets got attention. The confirmation of its size didn't come from a dedicated search for the largest star. It came from a team trying to understand cluster membership through radial velocity measurements. The galaxy is not a catalog we've finished. The zone of avoidance, the band of sky where the galactic plane blocks our view, hides a significant fraction of the Milky Way from direct observation. The most extreme stars tend to form in exactly the dense, active, obscured regions that are hardest to observe. Our census of what's out there is built on gaps. The history of this record reflects that honestly. VY Canis Majoris was 1,800 solar radii, then revised to 1,420. UY Scuti was 1,700, then the Gaia data cast doubt. Stevenson 2-18 is 2,150. Each revision has come from better instruments or better analysis, not from finding genuinely new objects, but from measuring existing ones more carefully. Which raises a straightforward question. How many Stevenson 2-18s are sitting in regions of the sky we can't see well? How many have been catalogued, flagged as anomalous, and set aside? We don't know. That's not a rhetorical flourish. It's a genuine gap in the data. There's a version of this story that ends with, "The universe keeps breaking records, stay curious." That's fine, but it's not quite the right takeaway here. The more specific thing is this. We don't know where the upper limit is, and we're not sure we would recognize it if we found it. The theoretical limit of 1,500 solar radii, the number that defined our expectations for decades, was calculated under specific assumptions about stellar structure and composition. Stevenson 2-18 exceeds it, and the response from the scientific community wasn't, "The limit is wrong." It was, "The limit applies to specific conditions, and this object doesn't fit neatly into those conditions." Which is reasonable, but it also means the limit wasn't really a limit. It was a model, applicable within certain bounds. So when we now say Stevenson 2-18 is close to the upper limit of possible stellar sizes, we're saying something that has been said before about stars that turned out not to be close to any limit at all. Maybe 2,150 solar radii is genuinely near the ceiling. Maybe there are stars in unobservable parts of the galaxy at 3,000 solar radii, or 4,000, that we haven't found because we can't see them. The vacuum density of Stevenson 2-18's outer envelope means the boundaries of star are already fuzzy. At some scale, it stops being a star in any useful sense, just a very hot cloud with a fusing center. What that boundary is, we don't know. What we do know is that every time someone has drawn that boundary with confidence, the universe has eventually presented something on the other side of it. Not as a dramatic revelation, just quietly, in the data, waiting to be looked at properly. Stevenson 2-18 was there for decades before anyone figured out what they were looking at.